protein activation such as NF-kappa B or the lysine 63 may be involved in DNA repair, etc. Okay? There's some other type of conjugation pattern is not well studied. Okay? So again, meaning that there's so much room for you and other young scientists to continue the effort. The lysine 6, lysine 27, 29, 33, etc. They are target for protein degradation or other type of process still remain to be characterized. Okay? But you get a sense. A 70 amino acid of the ubiquity have the lysine 6, 11, 48, 63, etc. And then the conjugation on different sites could have a different impact on that target protein's fate. Okay. And I want to go a little bit deep to tell you the cell cycle regulation, that many of these cell cycle regulation was indeed regulated by ubiquitination process, especially such as cycling. Okay, we talk about cycling A, B, cycling E, cycling D, etc. But here I want to point out to you the first one is cycling B. We talk about cycling B is such a process involving mitosis. And then here overview again quickly. The pro-metaphase, meaning the chromosome just condensed, was not lined up, metaphase, and then chromosome pulling into two daughter, the spindle cord right now is the anaphase, and then telophase, two daughter cell form. Okay. During this process, cyclin B is involved and then need to be degraded. Okay. Here, give you an example. This is cyclin B being labeled with a GFP. Just demark these white color as the green fluorescent of cyclin B. In the prometaphase, okay, cyclin B is still there, okay. When you look at the metaphase, there's no signal of a cyclin B anymore. Anaphase, cyclin B disappeared. This is a very simple experiment. Just at the beginning, many years ago, was done. This experiment was done just to prove to you the cyclin and this up and down regulation. And right now we know every cyclin is cycle. Okay. Here you take a look. Okay. Cyclin A. Let's start from G1 phase. Okay. This is G1 cyclin. Cyclin D and cyclin E. Cyclin D at the early G1, as you see here, they come out first. Okay. But they maintain a little bit longer and then going down in the mitosis. Cyclin E is late G1 cyclin. They come up a little bit late compared with the cyclin D, a late G1 cyclin. And then when the cell go into the S phase, they go down. Okay? Cyclin A is the cyclin involving DNA synthesis. And you can see the particular peak at the S phase and then going down during mitosis. Cyclin B is the one involving G2M progression. You could see them, they start peak at the mitosis, and then once mitosis finishes, they're gone. Okay? So right now you get the idea about the cycling regulation. They up and down because they are responsible for the cell cycle progression. Once the cyclin E finish at the G1S transition, they will be degraded. Once cyclin B is finishing up the mitosis, cyclin B will be degraded. Okay? So it's such an important process. And then why cyclin B need to be up, as you know, we talk about these are passive regulated to push the cell go through the different phases. Once they're done, they need to be degraded. How cyclin B degraded? Again, the E1, E2 is involved. The E3 for cyclin B is APC complex. We talked about that before. And then basically the APC complex add the ubiquitin of the lysine residue onto the cyclin B. And once the cyclin B got ubiquitinated, it will be recognized by 26 proteasome, and then protein got degraded. Okay? We already mentioned this, why cyclin B need to be degraded, because once the spindle fiber attach is complete, the cell might now give the signal, okay, we're ready to go to the anaphase. Okay, so the APC complex activated, degraded cyclin B. Okay, cyclin B degradation happened here. And I will tell you why cyclin B need to be degraded at the end of the lecture. Here, at the prophase, each part of the, actually mitosis, quite a few proteins need to be degraded because if you recall, that spindle fiber checkpoint, assembly checkpoint, so many proteins involved, including PLK, including arrow A, arrow B, cyclin B, etc. These proteins need to be degraded once the mitosis is complete. So let's take a look. The prophase, the APC complex, at the CDC25, the CDC20 as adapted. They will start working on the cyclin B. But at this moment, cyclin B is not degraded yet, okay? And the cyclin B and CDK has the capability to inhibit the separase. The security do the same job. It's a cohesion ring to keep the two sister chromatids together, okay? They won't allow it to creep. But once the cell from metaphase go to anaphase, these become activated. And then by now, cyclin B got ubiquitinated, securin got ubiquitinated, and then the securin got degraded, separates become activated. They'll create the cohesion ring. The cohesion ring got activated through sister chromatids and it starts separating. But APC did not finish his job yet. They have another adapter called CDH1, will be able to clean up all the protein involved in mitosis, including Arola A, Arola B, PLK, and plus all these other proteins, including the previous adapter, CDC20. CDC20 was here, but at the late stage of mitosis, CDC20 had to be gone as well. Okay? So, the protein finish their job, they will be degraded. At the end of mitosis, APC complex, clean it all up, okay? Now I'm going to tell you about cyclin D degradation. I have told you about the cyclin B degradation. Now is the cyclin D degradation. Cyclin D, as you recall, is an early G1 cyclin, and then again, it needs to be degraded. And the degradation signal coming from a very important kinase activity called GSK3 beta. Okay. As you can see here, okay, that cyclin D actually mislocated from the nucleus to the cytoplasm. If the activity of the GSK3 beta is activated. As you can see, this is a cyclin D1 alone. This is cyclin D1 plus another kinase together. Cyclin D1 is mislocated into the cytoplasm. But if the cyclin D1 co-transfect with the kinase STAT means these kinase do not have any kinase activity. The cyclin D, just like the non-transfected with the GSK3 beta, is still located in the nucleus. Okay? And then there the scientists find out GSK3 beta is responsible for a residue phosphorylation on cyclin D. This is threonine 286. Because if they mutated that particular site, even in the presence of a GSK3 beta, cyclin D is not mislocated. Okay? So here, cyclin D co-transferred with GSK3 beta mislocated in the cytoplasm. But if you mutate that site even there in the presence of GSK3 beta, there's no mislocation. Just you could see here. This is the bottom one actually is the dominant negative one. Not the dominant, it's the cyclin D with the threonine 286 mutation. So how this particular site is responsible for ubiquitination and degradation? We talk about sometimes the ubiquitination require phosphorylation event to make the conformation change. Okay. Here, at the beginning, the scientists try to understand how cyclin D may be regulated. So they're using the affinity column to purify cyclin D associated protein. In this case, they will be able to purify CDK4, of course, and then another protein come out called alpha B crystalline, okay? And then P21 is associated with cyclin D-CDK4 as well, as we know that this is a very important regulator for cyclin D-CDK4. To make sure this indeed is the interacting protein, they do a co-IP experiment. Who has done co-IP experiment? Raise your hand. Anybody do a co-IP experiment? Nobody has done, okay? So this is the biochemical way to identify protein association. Say you have a protein A, you want to find any protein associated with protein A, you will immunoprecipitate using antibody against protein A to do the immunoprecipitation. So any protein associated with protein A will be immunoprecipitated, and then you run on a gel. Then using the potential antibody that could be present in the immunoprecipitation complex, do a Western blot, and then you will be able, if you could recognize that means that particular protein is associated with protein A. We call this IP Western. Okay? Immunoprecipitation followed with Western blot. Western blot, sometimes we call the immunoblot. Okay? So remember this particular technique because this is very important to recognize protein association. So this is a technique was done here. It's called IP Western. Okay? Immunoprecipitate cyclin D1 first. So all the cyclin D1 associated protein will be immunoprecipitated. And then you run on a gel, run a protein gel, and then use antibody, say you already know alpha B crystalline is possibly associated with cyclin D. Right now you run a gel and then you're using alpha B crystalline antibody to immunoblot with the immunocomplex to see alpha B crystalline is present in the immunoprecipitation complex of cyclin D. And they found, yes, indeed, alpha B crystalline is present in the immunoprecipitation complex of cyclin D. Okay? I know this is probably a little difficult for those of you who never done the experiment. But remember this technique, it is very useful. If in the future you're doing any biochemical experiment, this is very, very useful. Okay. Here, they try to find out, in the end, they do some experiments to know that this particular site, the threonine 268, is important for alpha B crystalline to recognize. So they mutate that particular site and then do an IP Western again to see alpha B crystalline is still associated with the cyclin D or not. as you can see here, the wild type control, cyclin D1 still associated with the alpha B crystalline because IP Western showing that alpha B crystalline is present in the immunoprecipitation complex of cyclin D. But this does not happen when the cyclin D1 mutation, again, you immunoprecipitate these particular construct and then do the Western blot of the alpha B crystalline. There was no alpha B crystalline could be detected in the immunoprecipitation complex of cyclin D T286A protein, okay? Suggesting that alpha B crystalline is not able to associate with mutated cyclin D1. It could only interact with wild type cyclin D1. Okay? I will go a little bit detail about this, but don't, I know many of you probably have never done an experiment like this. The exam will not come out with too much about this, okay? But I think there is great opportunity for you to learn, okay? The purpose is to show you all these experimental details because you need to know how the scientists try to address the important question of the protein-protein interaction, of the protein target another protein's biological activity. Here, show you another important E3 ligase called FBOX4 is responsible for cyclin D ubiquitination and degradation. Okay. The reason we do that, we do a very important experiment for certainly we call it a house chase experiment. This is going to be difficult. House chase experiment. In the old days, we using the radioisotope to label the protein, okay? And then because it was house level meaning that only short-term labeling the protein, okay? So for example, you culture a group of cells, you feed them with a certain type of isotope. This isotope we call S35 methionine. So one of the building blocks of the protein. Methionine, remember, is an amino acid. It's a building block of the protein. But these methionine, the S residue, okay, has been labeled with an isotope called 35. So we call it S35 methionine. So you feed the cell with these kind of amino acid. All the protein, when they form or being built up, will incorporate this S35 methionine into the protein, right? Because if your protein need methionine, lysine, arginine, serine, etc. These proteins will have the methionine there. They will take up these isotope methionine into the building block. So your protein has been labeled with a methionine. Okay? And then only short label. Okay, so only that window you label the protein will be labeled. And then you wash away all these isotopes. And then feed them with the cold methionine, meaning non-radio labeled methionine. So in this process we call chase, okay? Chase with cold methionine. So this is so-called pulse chase experiment. Okay? Was able to follow the turnover of the protein. Okay? Turnover of the protein. Okay? Because you just follow the radioisotope originally made, giving some time, this protein may be degraded, and you will see the radioisotope disappear, right? So that's the important asset for you to recognize. So you can see here, this particular cyclin D1, if we pulse label it and then change with co-methionine, and then you find out the cyclin D1 originally been labeled with a certain amount, giving time, the band start disappearing because the protein is degraded. Okay, so you see the S35 labeling disappearing. Okay, so that's very important assay. Okay, and then if you transfect the cell line with this particular construct called delta F-FBOX4, this is a dominant negative form of this F-FBOX4, because the F-FBOX4 is already present in this cell line. The endogenous F-FBOX4 is present in the cell line, and then they will cause the downregulation of cyclin D. Right now, if we transfect a dominant negative form of F-FBOX4 into the cell, wipe out the endogenous F-FBOX4 in the cell, sort of inhibit the endogenous E3 ligase for cyclin D. Now you see, this cyclin D is very, very stable, right? Okay, you see from the band difference here. Here, following the time course, cyclin D1 disappearing, but here, cyclin D is much stable than the one you see in this particular cell. We do another thing by doing knockdown. Okay, everybody know knockdown, right? For those of you know knockdown, raise your hand. I only see 1, 2, 3, okay, 4, okay, great. Okay, knockdown technology these days is very important. That's because the shRNA been characterized. Short hairpin, shRNA called short hairpin RNA, was able to recognize a certain type of the RNA and then causing that RNA be degraded. So that we call it knockdown. So shRNA basically was able to knock down the gene expression of F-FBOX4. Okay, so now you see the cyclin D1, the pulse chase experiment. These, without knockdown, cyclin D1 has certain turnover. Okay, it's within 60 minutes, the half-life reduced, right? But the F-FBOX4 knockdown, the cyclin D1 is very stable. Now you get a sense that F-FBOX4 may be responsible for the cyclin D1 stability, okay? On the opposite, if we add the F-FBOX4, increasing the F-FBOX4, now you still see the cyclin D1 got downregulated because the increase of F-FBOX4, cyclin D1 got downregulated. So knockdown increases the stability of cyclin D1, but overexpression of F-FBOX4 causes the downregulation. You get a sense this particular protein is responsible for cyclin D1 degradation. Okay. Here, do the cyclin B knockdown, very similar situation that you see here, because alpha B cyclic, alpha B crystallate knockdown. Okay. Very similar situation like you see here, suggesting that alpha B crystallate is also responsible for cyclin D degradation and downregulation. That was a little bit detail about the biochemical study. But I think for those of you who have not done it, you should know and try your effort to learn the process. What is an IP Western? What is a knockdown? Okay, shRNA. Okay, so the model could be these type of things. Okay, we talk about the the E3 ligase at the SCF complex yesterday, SCF, okay, SCF complex, okay, in association with the E2 be able to transfer ubiquitin onto cyclin D, okay, and it's possible that FBOX4 by interacting with the alpha B crystallate will be able to recognize the phosphorylation form of cyclin D for causing cyclin D ubiquitination, thereby causing cyclin D degradation. Okay, you could come up with several types of models, okay, but you just need to provide more evidence to prove which model is correct. So as a scientist, a researcher, okay, you could base on your data to build up a model for your observation. Okay. So this is the model being built by the scientists who have done this type of experiment. They come up with another model potentially like this. Is it possible like this? It's a SCF